Welcome to question 6 of the 2011 Mathematical Methods Exam 1. In this video we will be looking at the solution and examination advice for this question. A reminder that this video is in no way endorsed by VCAA. For question 6 we're asked to consider the simultaneous linear equations as shown, where k represents a real constant. For part A we're asked to find the value of k for which there are infinitely many solutions. So if there are infinitely many solutions, we can represent that on a graph where one line will be exactly identical to a second line, which I'm just dotting on in orange. So that means the two criteria for infinitely many solutions are the same gradient and the same y-intercept. So if we consider this to be equation 1 and this to be equation 2, for equation 1 we can rearrange it into gradient-intercept form so that we can use our criteria to find the values of k for which there's infinitely many solutions. So we would have minus 3y equals, and we're subtracting away kx from both sides, so we're going to have negative kx plus k plus 3. So therefore y, if we get it by itself, we're going to do that by dividing by negative 3. So we'll have positive k on 3x plus, and then we're going to have k plus 3 divided by negative 3. For equation 2, we could have k plus 7 times y is equal to, and we're going to subtract away the 4x, so we're going to have negative 4x plus 1 on the right hand side now. So therefore y is going to equal negative 4 on k plus 7 when we divide by k plus 7, and that's going to multiply x plus 1 over k plus 7. So now we're going to consider needing the same gradient. So if we need the same gradient, that means that k on 3, so the gradient of the first line, must equal the gradient of the second line, which is minus 4 on k plus 7. Now rearranging that will give k times k plus 7 is equal to negative 12. So therefore k squared plus 7k plus 12 is equal to 0. And we've identified we're now solving a quadratic equation. And factorising that would give k plus 3 times k plus 4 is equal to 0. And to do that we'd look for the factors of 12 that add up to 7. And the null factor law would say that k equals negative 3 or k equals negative 4 are solutions to that equation. And now we need to consider having the same y-intercept. So if we start with if k equals negative 3, the y-intercept of the first line is going to equal negative 3 plus 3 over 3, which is equal to 0. And then if we consider the gradient of the second line, which is 1 over k plus 7, we'd have 1 over k plus 7 is going to be minus 3 plus 7, which equals 1 over 4. So therefore, as 0 does not equal 1/4, we get no solutions for that equation rather than infinitely many solutions. Then if we look at if k is equal to negative 4, we would have negative 4 plus 3 divided by negative 3, which is equal to negative 1 over negative 3 is 1/3. And for the second, we would have 1 over k plus 7, which is 1 over negative 4 plus 7, which is equal to 1 over 3. So as the two y-intercepts are equal, that is the value of k that gives infinitely many solutions. So therefore, when k equals minus 4, we'll give infinitely many solutions. So that is the answer to part A of this question. Now there are other methods for tackling this problem which are presented in the examiner's report, and we're going to do a second method of solving this problem at the end of the video if you want to see that done. So from the examiner's report, overall on question 6A, 25% of students got full marks, with 43% of students receiving 0 marks for that question. The following three methods are three different ways that can be used to identify and justify that k equals negative 4 is the correct answer. So the first method, which is what we did on the previous slide, was using the gradient and the y-intercept. The second method is using ratios, so comparison of coefficients as common ratios. And the third method, which we'll do at the end of this video, is using the determinant. And the additional comment in the examiner's report was that many students who tried to solve simultaneous equations rarely succeeded. And it goes on to say that whichever method was chosen, students had to justify their selection of k using their method. For part B, we have the same system of simultaneous equations, and we're asked to find the values of k for which there is a unique solution. So if we think back to a graphical interpretation of this, unique solutions occur when the two gradients of the lines are different, and the y-intercept is irrelevant. So all we need for this is different gradients. So we did previously find that if k is equal to -4 or k is equal to -3, we get infinitely many or no solutions. So that means if we select a value of k that is any real number excluding -4 and excluding -3, we will get a unique solution. So that is the answer to part B of this question. And just an additional note about this question to explore what we did find, when k was equal to -4, that gave infinitely many solutions. And that when k equaled -3, that gave no solutions, because we had the same gradient but a different y-intercept. And then for what we just found here, this gives one unique solution. And that occurs when the gradients are not the same, or they have different gradients. From the examiner's report, we can see that 33% of students got this question correct, and the examiner's report goes on to say that most students were aware of the two values of k, -4 and -3, that led to either no solutions or infinitely many solutions. The most successful approaches to these questions was using the determinant, which I'm going to show after this slide, and that many students chose a value of k that was not selected in their answer to part A, which was incorrect. We actually needed to exclude both -4 and -3, and k could be any real number except those two values for this question. So if we come back to part A, we're just going to see the setup for using the determinant to work out the values of k for which there are infinitely many solutions. So we can consider this simultaneous system of equations, and it can actually be expressed in matrix form as follows. So we have k minus 3 in these positions, and then we have 4 and k plus 7 in this position. So essentially we take the coefficients of x and y, and we put them in positions in a matrix such that when we multiply that out, we would get kx minus 3y and 4x plus k plus 7y. And we know that that is going to equal the values k plus 3 and 1. And now, as we discussed before, having infinitely many solutions is the same gradient and the same y-intercept of a line. And for a matrix system, what we want is to calculate the determinant is equal to 0. And that will give you either no solutions or infinitely many solutions. So if we have a matrix which is A, B, C, D, then we know that the determinant is going to equal AD subtract BC. So therefore, the determinant of this matrix system is going to be AD is k times k plus 7, minus BC, which is minus 3 times 4. So that determinant is going to be k squared plus 7k plus 12, and we want that to equal 0. So therefore, we get k equals -4 and k equals -3 as the two solutions to that equation. And then the rest of this problem would follow the same method that we used in the first slide, where we did it using the same gradient, same y-intercept argument. So you can look back there to see how we progressed from those two k values to finalising that k equals -4 was the value we were interested in.